Sure. Next. Now, the general solution for heat transfer through fins is like this. Okay? The general solution for temperature distribution through fins. Oh, the problem is I put white and I'm seeing where is the cursor. So, general solution for temperature distribution. Temperature distribution in a fin, in a constant cross section fin. Cross section fin. Okay, the constant cross section fin is theta is equal to C1 e power mx plus C2 e power minus mx, where theta is equal to t minus t of infinity, okay, and m is equal to square root of hp by hp by k into a of the cross section. Correct? Very important. I put c here because to say that it is cross section. Okay, p into hp divided by k into a cross section. I put it purposely. Okay, so m is equal to square root of hp by k into a cross section. Now once that is done, now in that fashion, what is the theta at the base of the fin? Let us take is theta b, theta base, theta b. Write it along with this, nothing great here. Theta b is equal to. We are repeating it, okay, but it's okay. One or two repetition is okay. So this is class number. This is 20. Today is 18th, is it not? 18th or 19th? 18th. 18th, 11th, 2022, 11:30. Okay, AM. Fine. So theta b is equal to TB minus T infinity. Is it? Now let us see one by one what are the cases. Let us see one by one how different things has to be done. I hope you have written this down for us. Let us apply the boundary condition. So C1 and C2 have to be found using boundary conditions. So one by one, different types of boundary conditions and different types of solutions. That's what we will see. Fine. Now, check. Now, in this fin, all the types what we are seeing, in this first of the things is there is first type of boundary condition is infinitely long fin. Infinitely long fin. If I have an infinitely long fin, then what is going to happen? Boundary condition at the base we know anyhow. So, what would be the boundary condition? condition at the base, at the tip, I say at the tip, theta at L is equal to TL minus T infinity, which would be equal to 0 as L tends to infinity. As L becomes very big, okay, or X length, tip as in this is the base, this is the fin. Now the fin is so big, so long, infinitely long fin, that at the tip of the fin, which is very, very long, T becomes equal to T. So that the theta at the end of the L, yeah. Okay, let us take this length as L. Okay, what did we take? We took the other length as L. Okay, then we will take this as small L. Let's change. Let us not change all the things. Let it be. Yes. Don't worry about the notation. We can change. The length become very high, long thing. Then what happens? You get the when it is infinitely long film, at the tip, it will be 0. It will be equal to T infinity. Correct. And what is uh, theta b boundary condition at the boundary condition at the base would be theta b is equal to, or theta is equal to theta b, which we can calculate t minus t infinity, t base minus t infinity. So what is the solution? So if you do that, if you see, look at it, let us see. So what is it? C1 theta, applying the first boundary condition. This is the first boundary condition. Applying first boundary condition. This is second BC. Okay. First BC. What we get? We get theta uh, L, which is equal to 0, is equal to C1 e power. We took minus or plus first. First one we took it as plus. Is it not? Yeah, plus. So theta e power plus mx. So this will be ml plus C2 e power minus ml, right? As L tends to infinity, this goes to 0, is it not? As L tends to infinity, e power minus ml is equal to 0, right? Right? No? So no. Clear with that. Therefore, C1, C2 will be 0. Oh no. C2 e power ml is equal to 0, right? So what would be C1? C1 will come as 0, correct? No? C1 will go as 0. Right? C2 will remain, which is minus, right? So, and C2 applying the second boundary condition, second BC, we get theta at base, theta B, which is equal to TB minus T infinity is equal to C1 e power ml, sorry, m into 0, which is equal to C1 itself. So C1 is actually equal to TB minus T. Makes sense? C2 is 0, C1 is 0, sorry, C2, I'm very sorry, C2, which is equal to C2. Okay. Apply your mind, students. C2 is equal to TB minus T. Clear? Let's go further with this. Now further going here. So what happens here? My t or theta would be equal to C1 which is equal to 0, C2 which is equal to t base minus t infinity into e power minus mx. Correct? So what happens? What is theta? Theta is t of x minus t infinity is equal to tb minus t infinity into e power minus mx, or t of x minus t of infinity divided by t of base minus t of infinity is equal to e power minus mx. Important question. Did we name the equation till now? Shall we name it? This was 7, right? This is 7 itself, so don't have to worry about this being 7. Right. Next we will go with this being 8. Right? This is about infinitely long fin. Now what is the heat transfer in this fin? Heat transfer. Heat transfer in an infinitely long fin infinitely long fin is Q is equal to minus KA into dt by dx, right? At x is equal to, yes or no? Why did I write like this? Because that is the heat going outside at the base. Whatever is going from the base, from this side, is going out here, is it not? If you calculate at the base, it's more than enough. So that is what we have done. Q fin, Q long fin, Q dot long fin. Is this? What is dt by dx at x is equal to 0? Dt by dx at x is equal to 0. We can write. See, I'll write over here, students. I'll continue here. So if you consider t of x minus t infinity is equal to t of b minus t infinity into e power minus mx. When you differentiate that, dt by dx would be equal to x, we will take here minus of tb minus t infinity, right, into e power minus mx. Yes or no? Correct? No, wrong. M is minus here. M is there, minus M. बरेच सर बरेच सर क्या अनेक अनेक ಸ್ವಲ್ಪ ಜೋರ ಏನೇ ಜಲ್ದಿ ಇಂಕ್ ಗಾಲ್ ಸ್ವಲ್ಪ ಇಂಕ್ ಟೈಮ್ ಬಿಕಾಸ್ आणि तालतू भीतर असा की इंक जॉब करायला लागेल अभी बरेच सर so now what is dt by dx? M. What is M? M is minus hp by kac and the root of it. Correct? And here we have e power minus mx at dt by dx, or dt by dx is equal to that into, I'll take the minus inside, okay? So if I take the minus inside, oh sorry, this is minus itself. Okay, fine. Minus dt by dx into tb minus t infinity to e power minus mx. What is e power minus mx at x is equal to 0? 1. So this will come as, so dt by dx at x is equal to 0 is equal to square root of, okay, square root of is equal to minus square root of hp by kac into tb minus t. Now we have to apply this back to the q equation. Write it down. Please write it. No, you can think. Don't worry. I'll give you time to think, but don't wander anywhere outside because I cannot see your thoughts. We'll give you as many time as possible to understand because we are actually clubbing preparation time as well as class time together. Okay, if you don't understand here, don't go outside without understanding. ಲೊಕೇಶ್ ಹಾಂ ಸ್ವಲ್ಪ ಭೂಮದಾಗಿ ಹೋಗಿ ಆಯ್ತಾ ನನಗೆ ಲೊಕೇಶ್ ನೆಕ್ಸ್ಟ್ ಕ್ಲಿಯರಾ ಅದಕ್ಕೆ ಕ್ಲಿಯರಾ
Sir,
yes please
there is no C there.
what C
HP by KA, there is no C.
KAC in the sense I'm saying cross sectional area okay it's subscript
Okay, subscript. Okay.
it means cross section area I've changed it if you want you can add here also cross sectional area okay so here you write cross sectional area so that there is no problem there is no confusion which area it is to be taken it is a cross section area kindly change it all through wherever we have used this this is H convection not cross section whereas here it is H cross section this would be H cross section makes sense this is H cross section makes sense correct convinced if you're not convinced I'll not go further boundary layer is not boundary layer we did not consider here which one this one you're talking about we are not boundary conditions we are talking about. Now infinitely long fin what happens now if you have a very long fin what happens at the end all the heat is transferred through this part does it not when it comes over here the temperature equals the temperature of the surroundings like if you use a long fin do you think the heat will reach there temperature will reach there no right so what is happening at infinitely long fin when you have infinitely long fin at the tip here this is very long here the temperature will be there some temperature if you put in red this will be red here then it will continue to blue green blue. It will be same as the surroundings afterwards which one T of L or theta of L you're talking about theta of L is equal to T of L minus T of infinity right that's what you're saying now this T of L will be equal to T of infinity so that's why it goes to 0 temperature at the end will be the same as surroundings, because heat from that infinite fin will not reach at the end. So what is happening? There is a, say there is a IC engine here, okay, which is heated like anything, and now you have a fin. The purpose of what is a fin? To remove that heat through the high surfacing area here. What I am doing, this is getting heated. Conduction is happening. Convection is happening. Convection is happening. Heat it is losing. If I make this very long, then what will happen? It will lose all the heat before it reaches the tip, is it not? So that's why if I use an infinite long fin, the temperature of the tip of the fin will be same as that of the surroundings. Right? Understanding important. Okay. I can spend any number of time. Don't rush into the things. Understanding here in the class, understanding is important. Fine. Online students, are you clear with me? Sir? Online students, is it clear?
Yes, sir.
Very good. Okay. So now this we are going to apply it here. Okay, this we are going to apply. So Q dot fin, Q dot of a long fin is equal to minus of KAC into dt by dx. Is it not? What is dt by dx we have got? Dt by dx we have got is minus root of h p by k into a of cross section into t b minus t infinity. Correct? Together what we will get? We will get it as root of q long fin q dot, the rate of heat is equal to square root of k ac or hp kac hp kac into tb minus t. Very important, these two equations. Most of the gate equations goes with 8 and 9 only. Most of the fins which comes in gate are 8 and 9. The long fin only they take. That's the easiest one. Calculation is less. So they generally go with infinitely long fin. Most of the questions that comes on gate is infinitely long fin. Makes sense? Done. Now, you can do anything further. Let us see next question. Done? Okay. Now, negligible or insulated tip is second one. Adiabatic. Adiabatic, second boundary condition which I am using. Adiabatic heat loss or adiabatic fin tip or insulated fin tip fin tip, adiabatic fin tip or insulated fin tip or 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 negligible or assumption or negligible heat loss from the fin tip. So you have negligible heat loss from the fin tip. That happens, what is the boundary condition at the field? Okay. So boundary condition at the base we know, right? It's always the same. The boundary condition, the first boundary condition, first we see the heat loss, okay, at the fin tip, at the fin tip, at the fin tip, d theta by dx at x is equal to L is equal to 0. This is the condition. Right? And what is the second boundary condition? Second boundary condition is at the base theta is equal to theta b, which is equal to tb minus t. That's first boundary condition. Now solving this, if you see that, okay. So if I say what was theta, theta was c1 e power ml plus c2 e power mx, e power minus mx. This was the thing. This was the general solution, right? This was the general solution. Now we are going to get the particular solution. So d theta by dx is what? D theta by dx is equal to m c1 e power mx plus m minus m c2 into e power minus mx. And if that is equal to 0, if that is equal to 0, it implies that I can write this as, if I do the whole thing, I can write, okay. So we have this one equation, so c1 e power mx minus c2 e power minus mx minus ml at x is equal to L. So x is equal to L. So ml, or I'll write here d theta by dx at x is equal to L is equal to, okay, ml, correct, is equal to c, correct. I'll write it like this. Okay, x is equal to L is equal to c. Fine. So this is the first boundary condition. So we can write, when we solve this, we get, okay, when we solve it, this is one thing. So C1 is equal to, yeah, C1, just a second, C1, C1 is equal to C1 raised to e power ml is equal to C2 into e power minus ml. And when we use that, C1 will come as, this comes here, or C2 is equal to C1 into e power 2 ml. This is one of the things. Write these down, students. What is another boundary condition? Theta b is equal to, we will use that in the next slide. Write this thing. Understand, right? Simple, this is simple. It looks complicated, it's not. Don't just copy, think about it. I think when you go out to other places, you should leave this habit of going slow, because other places that is not there. You will directly write, you call writing it. But it's okay, gateway will clear, then we will see. But this is how your learning has to happen. Learning has to happen like this. If 1 hour class is there, 2 hours of learning has to be there. In the way I am teaching you. Then you should not say class you have attended, 3 hours of class you have attended, and you're free to enjoy. No, don't do that in IIT especially. You have attended 3 hours of classes, 6 hours of learning you. Then you can do well. Otherwise, you cannot do. And don't keep it at the end. That is one of the main thing which is there. In IITs, if you keep it at the end, you're gone. VT ಉತ್ತರ ಆಗುದಿಲ್ಲ. Because that amount of studies is required. Keep in mind, you are doing one of the most difficult uh, studies in across all the disciplines of study. Engineering is not easy. Engineering is not like other type of degrees. It's similar to being a doctor, being a lawyer. They don't do work, but still they have to do any profession. They have to do, but this is demanding because best of the people are coming here. The competition is there. In engineering, the people who are the best will come here. Is it not? Chalo. No, dx is this part. This is x from here. So at this point, what is the slope of the temperature? Here there is no heat transfer which is happening. So what should be the slope of the temperature? Temperature drops. But then the slope will be zero over here. That's what it means. So temperature here, you say theta B, and here you say theta at L. You will have some numbers. Theta L will be there. It will not be zero. But the slope here will be zero. At the tip. At the tip, there is insulation. It is very, very long. There is no insulation. But there, theta L is equal to 0. In the previous case, if you see here, what is happening here? If I say this is theta, what is happening? It starts from high, theta B, and it goes to 0. Yeah. So theta B is what? Theta is what? Theta is T minus T infinity. So if T is equal to T infinity, theta will be 0. Makes sense? Here theta is not equal to 0. It has some non-zero point. But there is no heat transfer because there is insulation. So you cannot have, I'm sorry here. Yeah, here you see here this is having zero profile, zero slope at the end. Makes sense? Fine. Understand. I can go any slope. When we do a topic, that topic should be such that any question coming on that, you should be able to answer. We are preparing you for the worst. Think all the topics. It's difficult question only. And if that happens, the maximum marks will drop down from 90 to around 40 or 50. Everything is difficult. At that time, even if you score 35, 40, you will be on the top. So we cannot say anything. Maybe the passing mark will come out to 15, 16. No, I'm telling you the worst thing. This can happen. It will not happen. But still, in case it happens, you can drop down to 15 is the passing mark. Everything is difficult. Okay. You have to judge that based on the question. Done? Done? Next. Next question. Next continuation of this. So now what happens here? So also, if you consider theta base, right? So if you consider theta base is equal to TB minus T infinity, which is equal to C1 into C1 into e power 0. X is equal to 0, it will become 0. 1 plus C2. So C1 plus C2. So we have two equations. This is second boundary equation. Okay, you need the book here? Yeah. Thank you. Sorry. Okay. Theta B is equal to TB minus T infinity, which is equal to C1 plus C2. Right. So what is happening here is first equation we have. So we have two equations. C1 is equal to C2 is equal to C1 into e power 2 ml. C2 is equal to C1 into e power 2 ml. And we have C1 is equal to C2 into this. So we'll apply that. So theta B is equal to C1 instead of C2, I will put C1 into e power 2 ml. Makes sense? So what I'll have C1 into 1 plus e power 2 ml, right? Or C1 is equal to, or C1 is equal to theta B divided by 1 plus e power 2 ml, and C2 is equal to C1 into e power 2 ml. So that is equal to 1 plus uh, just a second, I made a mistake. I suppose. Okay, just a second. Students. One second. Okay, let us write this as C1 into C1 is theta B into e power 2 ml divided by 1 minus 1 plus e power 2 ml. Right. Now further, let us multiply it and divide it by t power minus 12. Okay. So C2 can be equal to, you should multiply and divide by e power minus 2 ml. So this will be, you multiply by e power minus 2 ml and you divide by e power minus 2 ml. If you do that, you will get this as C2. You will get it as theta B. This will become as 1, so don't have to worry. So this will add up divided by e power minus 2 ml plus 1, or C2 is equal to theta B divided by 1 plus e power minus 2 ml. Fine. Two things we have got. Make sense? So C1 we have got, C2 we have got. Right? So come. C1 plus, yeah, theta B is C1 plus C2. Agree. There what we did, we wrote C2 is equal to C1 into e power plus 2 ml. How did we get that? From the first boundary condition. Differential equation ಮಾಡದಿದ್ರು ಇದು ಮಾಡುವ differential equation ಸ್ವಲ್ಪ ಸಿಗ್ತದೆ. You understand how the differential equations has to be applied. ಇದು second, third ಅಷ್ಟೊಂದು important ಅಲ್ಲ. Second, third, fourth. Still we will do it as a practice. In terms of first one is only enough, most of the questions. Wrong. That is the most of the things will come. If it was, I was there in In other institute, they will do first one, and the second, third, fourth, they will give you the formulas. We will derive it, okay? Because our aim is not just to write it and we have to get a feel. Is it not? Sagar is not there, but still. No, I used to use that feel before only. Not after Sagar has come, we have used that. Then, ಈಗ ಇದನ್ನು ಅದರಲ್ಲಿ ಅಪ್ಲೈ ಮಾಡಬೇಕಷ್ಟೇ. What we will do then? I'll go a bit fast. This is not that important. So here we can write, see. So we get theta is equal to baby. So I can. Next. Now theta. ಆಯ್ತಲ್ಲಪ್ಪ ಬರುತ್ತೆ. Theta ಏನಾಯಿತು? Theta is C1 e power plus ml. So C1 is equal to theta b divided by 1 plus e power 2 ml, and here we have e power 2 ml, right? Plus into 2 ml, oh sorry, 2 mx, correct? E power 2 mx, correct? Even e power 2, not 2 mx, mx. I'm very sorry. It is e power mx, correct? It is e power mx, correct? Just a second, students. Correct. We are applying that there. Plus, we have theta b into e power minus mx divided by 1 plus e power 2 ml. Correct? C1 and C2 correct? No? Minus. I'm sorry. Minus 2 ml. Correct? No? This is the solution of theta with respect to x. Now this can be t of x minus t infinity divided by t of base minus t infinity is equal to is equal to is equal to is equal to e power mx. This is minus, is there? No, right? It is correct. E power minus mx. E power mx uh, plus e power minus mx. E power mx plus e power minus mx divided by 1 plus e power 2 ml and 1 what have you made a mistake here? No. 1 plus e power minus 2 ml. Correct or wrong? No, it's wrong. It's wrong. It's wrong. So, yeah, we have to do like this. Okay. You have to write e power mx into 1 plus e power minus 2 ml plus e power minus mx into 1 plus e power 2 ml divided by 1 plus e power 2 ml into 1 plus e power minus 2 ml. Correct? Okay. So now, further doing this, you will get this as e power mx plus e power minus 2 uh, ml minus mx plus e power minus mx plus e power minus mx into minus plus 2 ml. Okay, this is what we will get divided by, when you multiply this, what is plus here? Here mx plus mx. Yeah, here it is plus mx. Correct. So further going like this, I will not do the derivation here full, okay, because it is taking more time in algebra. We will not take. This will become 1 plus 2 times uh, 1 plus 2 times 1 plus ml, 1 minus ml is not there, is it not? So yeah, let us have 2 times e power 2 ml, e power minus 2 ml, which will give us 1, right? Plus e power, when you multiply both, is it not? No. Yeah, you cannot do it like that, is it not? It is not 2 here. This is 2 here. Fine. 1 here. Okay, wait a minute. Let me do it. So 1 plus e power, wait, 1 plus e power minus 2 ml plus e power 2 ml plus 1. Correct? 1 by, that's also possible. What we will get? Huh. Huh. Okay. Okay. I understand. I understand. We could have done that. Agreed. Okay. So now we will go like this now. Okay. That we have got like this. We'll go like that. Okay. So this will come as, if you consider e power mx, e power minus mx. Here what we will get, we can take e power mx outside. If I take e power mx outside here from the full equation, what you will get? You will get, should we take e power mx? Yeah, e power mx outside from this equation. You will get 1 plus e power minus 2 ml. Here 1 plus plus 2. No, no. Wait, wait. So here, does anything cancel here? Yes, it does cancel. Wait a minute. It does cancel. Wait a minute. Wait a minute. Wait a minute. So here, minus mx. Observe. Here e power minus mx. This I will write it like this. Okay. So e power mx plus e power minus 2 ml plus e power mx. Can we write it like this? Yeah, into e power mx. Okay, but that will come the same. Wait a minute. We cannot write that. We have to do that. Have we done some mistake in doing this? Okay, you do the calculation, students. At the end, what we have to use is, I will tell you what the end result comes. Okay, see, cos h of x is equal to e power x plus e power minus x divided by 2. Using cos h is equal to e power x minus e power x plus e power minus x divided by 2, we obtain tx minus t infinity divided by tb minus t infinity is equal to cos h of m into L minus x, and here you get cos h of ml. This is what we get at the end. I will, you do the algebra, students. This is the final result what we get. So I think here in algebra we have done some mistake. Till here it's proper. Till here it's proper. Okay, even till here it's proper. Even till here it's proper. Then you have to do the algebra to get it to that place. Okay. How can we do that? Yeah, we can group e power mx and e power mx. You can group this and you can group this. Then you will get. And down you will have this being grouped. Okay, here you get 2. 2 plus e power minus 2 ml, e power plus 2 ml. So we have to use some algebra. But anyhow, don't worry. I'll write the equation for you. Okay, you can derive that. There's no problem in that. I will not do the derivation. Okay, because algebra there is a lot of algebra there. It becomes really complicated. Okay, so final, this you have to remember. Remember, this is equation number 10. Remember, and this one you remember. In general, this is you have to remember in general. Okay, sine is e power x minus e power minus x. That has been. So this is in general you have to remember this because we are using this in differential equations also cross section. Yeah? Now similarly, now next you find out what is q. The next one is q. Based on this, you can find out q. Okay. So we have to differentiate. There is a differentiation which comes. So I will not do the full thing. Algebra is over to you. Okay. You've written this down, Bharat? No? One second. And now similarly, we'll go next. See what is q dot for a adiabatic tip is equal to minus ka into dt by dx at x is equal to 0, which comes out to be equal to square root of hp, h into perimeter, into k into area of cross section, into tb minus t infinity into tan of hml, tan of hml. Remember this, students. Let it go into your formula sheets. Although not much is asked, but still, why take chances? Is it not? Why take chances? Even 1 or 2 marks matters a lot. Just a second, I'll just. ಏನಾಯ್ತು next thing, third one, which is uh, specify temperature fin tip. Third one is fin tip with a specified temperature. With a specified temperature. That is TL is equal to T tip. If they give the specified temperature at the fin tip, then what happens? So, first boundary condition at the fin tip, at the fin tip would be equal to theta of L. Theta of L, this is small l, no? I'm sorry. Theta of L is equal to, theta of L is equal to, huh? Tip, T of tip. Okay, makes sense? No. So this would be TL minus T infinity. Okay, and second boundary condition would be at the base, at the fin base, theta B, theta at x is equal to 0 is equal to theta B is equal to TB minus T. Both are specified. So here the temperature distribution after getting C1, C2, everything, okay, we will get the temperature distribution is given by the temperature distribution distribution is obtained as T of x minus T of infinity divided by T of B minus T of infinity is equal to T of L, T of L minus, I'll write here, T of L minus T of infinity divided by T of B minus T of infinity into sin h mx plus sin of h m L minus x divided by sin h m L. Makes sense. And our Q dot, this you write as 11. No, this is 10, is it not? So let this be 11. Okay, let this be 12. So the derivation will take a long time. We will not do it. We will follow like other gate coaching institute what they do. It will take a long time in deriving these things. Okay. So Q for specified Q dot for specified temperature is equal to root of, okay, that is equal to, okay, that is equal to root of HP KAC into TB minus T infinity into cos of H ml, cos H ml minus TL minus T infinity divided by TB minus T infinity divided by divided by sin h, sin h. This is the Q specific. Both are important students. 30. Both are. Let this go in your formula sheets. Done. Next. Fourth one is convection from fin tip. There is convection from the fin tip. So what is the boundary condition? Boundary condition. This is very important, friends. Boundary condition is at the tip, at the tip, at the tip, Q dot due to conduction is equal to Q dot due to convection. Make sense? Boundary condition is Q dot due to convection is equal to Q dot due to convection. That is what happens. So what will happen? Minus K into AC dt by dx at x is equal to L is equal to h into AC into T of L minus T infinity. What happens? AC cancels. And what you get is dt by dx at x is equal to L is equal to minus of h by k into TL minus T. Applying this boundary condition as well as the base boundary condition, the temperature distribution is obtained as T of x minus T infinity divided by T of B minus T infinity is equal to cos h m of L minus x minus plus h by mk sine of h sine h m L minus x divided by cos h of L is small l, I'm sorry, small l, no capital L here, cos h ml plus h by mk sin h ml. This you write it as equation number 14. Let this be equation number. There's no mistakes students in this, don't worry about mistakes. Everything has been written precisely correctly. Very complex, is it not? It's very complex. That's understood. We will have answers for that. I mean, what is complex, we can make it easy. But we should have a confidence to handle complex things also. Okay. But anyhow, not much. First one only, if you remember, it's enough. Okay. This you remember. You can remember, it's well and good. If you don't remember, don't worry. I'm not saying it will not come in good, but chances of coming on the basis of whatever has come is less. Done? And GATE does not want you to remember a lot of things. They want you to remember concepts, not formulas. So don't worry about it. They're not testing your memory, they're testing your understanding. That one thing you have to understand in GATE. Never they test your memory. They test your concept, which you understand. Then, right. Convection from the fin tip is still fin is small. See, what are the different type of things that we can have? All the conditions are covered here. So, first one is the fin is very long. So at the end there is no heat transfer also. That's the first thing. Second one is fin is short, but it is being insulated. So when the fin is insulated, what is going to happen there? There is negligible heat loss from the fin tip. Correct. Third one, the last final part of the fin is maintained at a particular temperature. That can happen. The fins can be between two pipes, where one side one temperature is there, other side other temperature is there. That's the third case. Fourth case is leave everything. It's not a long fin. It is not insulated. So from there can be heat transfer. So then what? Huh? Area will be. Hey, I'm very sorry, Pa. She. I'm very sorry. This is a big mistake. Big mistake. Big mistake. Yes. You cannot cut it like that. No. Wrong. This is wrong. I cannot use C here. It is area of convection, which is different. This area H can be written as H P into L. Very short. Perimeter into length, is it not? So no. Even that is not correct. The tip only. Yes. So we have to write area. It is the. Oh no. Wait a minute. Same thing. Yes, it is. Correct. Correct. It's the same thing. I'm very sorry. You can cut. I'm sorry. Yes. Yes. Tip it's convecting, is it not? Yeah. You can cut. Convection at the tip. Do ask these questions, but okay, there is convection. So sometimes I also land in a lot of confusions. It is a convection. The tip is there. From the tip, the convection is happening, not from the periphery. And the conduction is also happening to the tip. Correct. This is correct. Chalo, done. Clear. So all the four cases. Are there other cases which can happen here? Heat transfer. Heat transfer in this case is see. It's half the tip. It is not very long. It is not insulated. Okay. See, first case is what? Very long. Very long. What's the second case? Second case not very long, but I've insulated here. Huh? There is no expression for theta. Yes. There is no expression for theta. In the sense you want expression for theta, this would be theta L. This would be d theta by dx at L. X is equal to L. Makes sense? So T can be, okay, if you want to put it in terms of theta, this would be d theta by dx at x is equal to L would be equal to minus h by k into theta L. Correct? Because our governing equations are in terms of theta. Fine? Clear? So second case is over. Third case is over. where you have different temperature here. This is the temperature. This is different temperature. Fourth case is you don't have any of the four. It's a small fin. Makes sense? There is convection from the tip. There is convection. Right? No? Fantastic. That we won't have it. Instead of having that, we could have not have a fin at all. See, in case you are right. Okay? In case he's understanding you. Okay, I appreciate your response. The next thing is, sir, let us insulate everything. The fin itself will insulate, and from here only the heat transfer can happen. But then the purpose of the fin is itself is lost, is it not? Yeah, yeah. Let this be here only. Why to have a fin, then have an insulation? Uh, the area. Uh, yeah, here we are taking the whole thing as the constant uniform cross section. The whole case is of uniform cross section. Which one? This area and this area. It is the same. This is a fin of uniform cross section. The whole thing we have started is we started it here. Fins of uniform cross section. For which one? For the last one? No, no, no. See, at the end, when there is a convection from the tip, what is happening? Where is the area of this one? It is from the tip only, is it not? Last one from the tip, there is convection, is it not? Here and all convection we have considered. But as a boundary condition, there is convection from the tip, is it not? It is convection. Correct. Read out here. Imagine. All the four cases of the fin are over. Fifth case, you put the tip, you have the insulation to the whole fin, and you have this one. Then you don't have to have the fin at all. Let us not have the fin. Is it? The purpose of the fin is lost. Are you able to imagine, students? See, first one is very long fin. Is like it's very long, so we can use that. Okay. Second side, when you say insulated tip, if it is there, maybe places where you don't want it to, from there you don't want heat to pass. At the end, you don't have the heat. There is no heat source there. You don't want the heat to pass. There are situations where such kind of things happens. Okay. Maybe there is a wall, like if you say a fridge. Okay, there is a wall which is there, and you don't want the heat to pass to the other side. You might have a heat exchanger. You might have a fin which is given to the heat exchanger, and at the end there is a wall. You don't want heat to come out of that. You want heat to pass only through here. Then you insulate the tip. For example, let me write this. Then one by one, everything I will explain where and all it is used. Okay. Next. Next one here. Last one is Q with convection at the tip. Q dot with convective tip. Convective tip. I'll explain you all the things where it is used, students. Let us write the equation first. Is equal to minus Ka of cross section dt by dx at x is equal to 0, which gives us Q convective tip. Online students, I hope you are following, and I have not muted you. Yes. Okay. So this would be equal to square root of HP K AC TB minus T infinity into sin H ml plus Hy mk into cos H ml cos H ml divided by cos H ml plus H by mk into sin H ml. Okay, this is the fine. Now there can be, it will be a thin film. It will be a thin, which we use in AC's backside. We use a thin film. Okay, at the end, the temperature may be almost zero. Okay, that is a thin film which we are using. You have a closely spaced fins. You see that? Okay, which is in AC, the aluminium one. But the point, that is a thin film. Okay, that is one reason. A lot of ways in which it comes. I will tell you one by one what are the reasons where it is used. You would have seen fins like anything, students. Okay, but you would have realized that that is there. That I will tell you now. Huh? That, that is the fin which is used in swimming. That is hydrodynamic lift you are creating. That is different. For lift purposes. That is hydrodynamic. It is the fin here is to increase the heat transfer. Then now next. Here one of the approximate V. This is a very complex thing, is it not? General. Okay. An approximate method to solve 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 approximate method, but still accurate, still very accurate, very accurate in the, not very in the sense, still practical. Okay, still very accurate and practical. Okay, way of accounting accounting the heat loss from the fin tip. This is important, is being asked. Okay, fin tip fin tip fin tip is to replace, this is important students, is to replace the fin length, L in the relation of the insulated, in the relation fin length L, replace the fin length L in the insulated tip case case by corrected fin length, defined as L corrected LC is equal to L plus AC. P is the perimeter. Very good. So equation number, this equation is important. Students. There has been question directly on this. Okay. So here 14, 15 and 16. 15 and 16. Right. You use the corrected fin length and use this in the insulated tip condition. Okay. Insulated tip condition is a bit easier, is it not? So you can use it in an insulated tip condition. You can use it. Done. Now, I will turn this down. I will run. Done. Now, for a rectangular fin, L corrected. For a rectangular fin, for a rectangular fin, L corrected is equal to L plus thickness by 2. The thickness, what is that? Divide by 2, you get that. Length is anyhow that. Okay, and for a pin fin or a circular fin, for a circular fin, LC is equal to L plus D by 4. L is small l, I'm very sorry. L, L, L. That if you add to the length, then you can use it as a in the insulated tip condition. Which one? It is applicable. It is applicable. This is. I'm not saying it's not applicable. This is a. Yes. It's the same thing. Because here we have taken area of cross section. We are taking area for even if it is trapezoidal, rhombal, everything you take. Area of cross section, we are not saying it is rectangular or whether it is. We are not taking that at all. Even in the calculation, you might have seen that we have not considered which type of area it is. See, wherever is the area of cross section, did we consider anywhere? No, easy. Start from the initial general solution. Here, what did we do? A, perimeter, P. Perimeter can be anything. Makes sense. From the first only, we have not considered which type of thing. Here we have used dx, but the dx could have been used for a cylindrical also. Makes sense. It can be used for, say, full gobi type of. It can be flowery fin. I don't know if flowery fin exists or not. But if in case you're good in drawing and you make a fin like this, flowery fin, and you use that. They use it in fact. They use those kind of things. Star type fin they use. And they use from starting till the end. You need not have rectangular. You can have a star cross section also. Correct. Yes, very much. Yes, but then there are cases where circular is the best. Circular will become cheap. It's always economic. It's not just heat transfer only. Along with heat transfer, economy also matters a lot. If you get small rods easily and cheap, you use it, is it not? If instead of making a complex shape, which will take a lot of efforts, or manufacturing time and manufacturing cost is there. So if you something is manufactured at a low cost, you can use it. So it is the engineering what do you say decisions are not just based on one criteria. There are number of criteria which come into picture. Ease of manufacturing, assembly line, then maybe vibrations. A lot of things comes into picture. Okay, engineering system is not easy to design. It's very difficult. That is why the people who are product designers are paid like hell, because only two things helps in a company to earn. One is marketing, one is products. If your product is good, company is good. Marketing is good, company is good. If the marketing is good and product is not good, it will not last long. Initially, you may reach a lot of people, but in similar way, everybody will tell that the product is not good, and your company will not have much revenues in the long run. If a company has to sustain for a long time, product also has to be good, marketing also has to be good. If product is good, marketing is not good, it will take a long time, but there is no failure if the product is good. Get that point? Until and unless a competitor comes. If a competitor comes, then gone. That's why the marketing has to be faster. To develop a product, marketing has to be faster. Marketing is important. Unless and until the product is like what Ananth Pai is giving. Here, I don't have to worry about competition. I can always grow. You understand? This is not replaceable. Ananth Pai is not replaceable. Why it is not replaceable? Because once, okay, it's okay. We'll not worry about it. You can replace, but it has to be my student. The student can replace it. Okay, not us. Okay, sure. Done. And for that, I am happy if that happens. Okay, so we continue. Next, fin efficiency. Very important. I've told you before, fin efficiency and fin. This I'll come do it in the next class. Okay, I will try to do. Now I'll tell you what are the cases where these are used. So in case you have a long tube, say this is IC engines. Instead of that, I use a very long tube. Okay? Sometimes we use it, and it is open to the atmosphere. Very long but thin. This kind of fins are used. Then this can be considered as an infinitely long. Generally, it is in case of L by D ratio of 8, more than that, we consider it as a long fin only. Okay. Next one, in case you have this fin tip and you don't want heat transfer to happen, you insulate it so that here there is some other processes which should not get affected by this. Then you insulate. Why do you insulate? There are other processes. I don't want heat to reach here. So then you insulate and you have heat transfer because of air being transferred like this. This is the fins which are there. A lot of fins are there. You insulate so that the heat transfer should be in one side only. Then that's an insulated tip condition. There are various places where this will happen. Second, third, next one is long fin. Yeah, long fin. Then you have insulated fin, and then the next one is temperature. Yeah, temperature is required. Suppose you have a heat exchanger. Okay, you want it to. You have one two steam pipes, for example, maybe a steam pipes or anything. Okay, there might be a fin which is connecting these two pipes. It needs heat to be transferred. Maybe it is condenser or something like that. I don't know. But sometimes these are connected to places where temperature will remain constant and the heat has to go off. Then you use this. Or maybe sometimes in boilers also we have that. In boilers also, sometimes such kind of things are used. Okay. Anyhow, whatever be the case, one side there is one temperature, there is other type, other temperature. There are applications where this happens. Then it is a particular temperature at the floor. Third case is a general case. Sorry, last case, the fourth case is the general case. Bike it's, but there it is not of the uniform cross section. What they use? They use a cross section which is tapered cross section. You see that? So it increases complications. You understand in design, okay? But otherwise it is good only, okay? Because you need air to reach at the bottom position. So that is why they use a tapered fin. So that, and it has a lot of the angle also is very important. Everywhere the calculation is important. Optimized one. Where you keep the engine is very, very important. How it is cooling is very, very important. Which one? 4 and 2. Actual fins, these are all actual fins. In the ಯಾವುದ್ರಲ್ಲಿ ಪ್ರಾಕ್ಟಿಕಲ್ ಎಲ್ಲಿ ಯೂಸ್ ಮಾಡೋದು ಪ್ರಾಕ್ಟಿಕಲಿ ನಾಲ್ಕು ಇದು ಕೂಡ ಯೂಸ್ ಆಗ್ತದೆ all the four cases are practical cases application all the four are practical conditions used in some or the other places. So we'll stop it here, students. We will use fin efficiency and fin performance.